Well, let's continue on. We did doubling. Let's do halving. And again, we're going to use the neutron example. We start with 4 times 0. And at some unknown time, we get 2. So that unknown time is the halving time. Now, let's write this out. So the process is using E, but it's with a negative power because that's reciprocal. So things are decaying away. We've seen that in other videos. So when this is equal to a half, which we write as 2 to the power negative 1, we can write then 1/2, or 2 to the negative 1, as e to the minus 0.693, and that number goes on. And then this equality only holds if AT is 0.693. The minus signs cancel, divide, and we get the same formula as we got before. Just we have minus signs everywhere because we're talking about reduction, decay, in this case, halving. So that's what we get.
That's very curious and beautiful. So I think we can look at an example of this. Just like our previous part, when the decay rate A goes down, then it takes a longer time for the neutron population to halve. But on the same timeline, if we had a higher decay rate, so things decay quicker, then we get a shorter time interval between these decays happening. Does that sound right to you?
Yeah, and in fact, that's what we're going to do when we talk about half-life. If we have radioactive material and decay modeled by this math, this is exactly what's called the halving time, or the half-life of the radioactive isotope.
And you're not talking about the game, are you?
No, I'm not talking about the game. This is pretty serious stuff, unfortunately.
Got excited.